Pluto, the mysterious dwarf planet located at the far reaches of our solar system, is generating enthusiasm within the astronomical community. Recent findings suggest a potential encounter with Neptune, raising concerns among scientists and space aficionados alike. Notable experts, including Neil deGrasse Tyson and Michio Kaku, have issued warnings about the possible ramifications of this celestial confrontation. But how did Pluto find itself on a collision trajectory with its remote neighbor, and what could this cosmic impact signify for us here on Earth? Let's delve into this evolving situation. Once regarded as a full-fledged planet, Pluto was subsequently reclassified as a dwarf planet due to its distinctive orbit. Despite this alteration, it continues to fascinate and engage astronomers. Recent forecasts from leading scientists emphasize a troubling closeness between Pluto's trajectory and that of Neptune. These authorities caution against a potential clash between the two planets, posing a significant risk to Earth. Pluto's voyage around the Sun is characterized by its unparalleled features within our solar system. Its orbit spans an extensive 248 years, and since its discovery in 1930, Pluto has yet to complete a full circuit. Adding to its allure is the highly elliptical shape of its orbit, which differs from the nearly circular orbits of the major planets. Furthermore, Pluto's orbit is tilted at 17 degrees to the ecliptic plane, making its path steeper compared to other planets. A notable characteristic of Pluto's orbit is its intersection with Neptune's trajectory. For approximately 20 years during each orbit, Pluto ventures closer to the Sun than Neptune, defying expectations based on their relative positions in the solar system. So why hasn't a collision occurred between Pluto and Neptune? The answer lies in the gravitational influences exerted by other planets. The study of Pluto's orbit began shortly after its discovery, revealing a perplexing trajectory for astronomers. Unlike most planets, whose orbits align relatively closely to the ecliptic plane, Pluto's distinctive traits include a steep inclination and an elliptical shape. The enigma deepened with the realization that Pluto's orbit crosses that of Neptune. The stability of Pluto's orbit amid these complexities serves as evidence of the intricacies inherent in celestial mechanics. The three-body problem involves understanding the motion and gravitational interactions among three celestial entities, such as Pluto, Neptune, and the Sun. This issue sheds light on the intricate interplay of their paths and gravitational forces. Terms like AIML, libration, latitude libration, and KAM oscillation help unravel this cosmic puzzle. Astrophysicists assert that libration, which helps maintain planets in their orbits, plays a crucial role in the context of Pluto and Neptune. This term indicates that when Pluto intersects Neptune's orbit, it is positioned at least 90 degrees away from Neptune, thus crucially preventing potential collisions. Latitude libration ensures that when Pluto approaches Neptune or other giant planets, it is situated significantly above their orbital plane, providing an extra layer of protection against impacts. The KAM oscillation explains why Pluto's orbit around the Sun appears unusual but remains smooth over time. Despite apparent randomness in space, numerical simulations conducted in the late 1980s revealed that, despite stable attributes, Pluto's orbit is technically chaotic, with minor initial deviations leading to significant changes over millions of years. However, Pluto's unique orbit maintains stability over incredibly long time frames, keeping chaos in check. Recent computational tests have improved our comprehension of how large planets like Neptune, Jupiter, and Saturn influence Pluto's trajectory around the Sun. Neptune's unique relationship with Pluto, completing 3 orbits for every 2 of Pluto, significantly bolsters the stability of Pluto's orbit. Additionally, Jupiter's immense gravity exerts a considerable influence, while Saturn's impact, though lesser, also plays a role. Through comprehensive analyses, scientists have demonstrated that the combined effects of Neptune, Jupiter, and Saturn ensure the safe and stable movement of Pluto in space for billions of years. These phenomena are essential for maintaining the order and predictability of celestial movements in the universe. Without these mechanisms, the solar system would be susceptible to greater chaos and unpredictability, potentially leading to collisions or ejections from stable paths and causing ripple effects on other celestial bodies. Understanding Pluto's orbit is particularly vital amid discussions about a potential collision with Neptune in the future. This knowledge offers a clearer understanding of the dynamic nature of the solar system. Pluto's situation highlights how seemingly unstable orbits can attain equilibrium through the intricate interplay of gravitational forces and orbital mechanics. Continuous observation and study of these phenomena are crucial for gaining a better grasp of our place in the universe. Exploring the vastness of space often reveals the unpredictable nature of celestial bodies, and Pluto's orbit serves as a prime illustration of this unpredictability. The concept of orbital chaos vividly illustrates the sensitive dependence of a celestial body's path on its initial conditions. As shown in Pluto's case, even slight variations in the dwarf planet's position or velocity can significantly modify its long-term orbit. Computer simulations have been pivotal in aiding scientists in understanding how Pluto navigates through space. By making minor adjustments in these simulations, astronomers can observe how small tweaks can have a substantial impact on Pluto's trajectory. In the late 1980s, these simulations revealed an intriguing aspect of Pluto's path. Despite factors like AIML and latitude libration contributing to its stability, Pluto's orbit can still exhibit unpredictability. Even a minuscule initial difference in Pluto's position or velocity can lead to significant alterations in its path over many years. Despite this inherent chaos, Pluto's orbit remains stable for an exceptionally long duration, extending over billions of years. This suggests that beneath its seemingly erratic appearance, Pluto's journey around the Sun follows a structured order. Predicting cosmic events, particularly with planets like Pluto that have unpredictable orbits, is quite challenging. The inherent unpredictability of these systems makes long-term forecasts uncertain. Numerical simulations assist us in understanding and anticipating the future trajectories of celestial bodies, but they also reveal the limits of our predictive capabilities. These models heavily rely on accurate initial conditions and simulate complex interactions. Even a small error can lead to significantly different outcomes, complicating precise predictions. The unpredictable characteristics of celestial orbits, such as that of Pluto, serve as a reminder of the constantly changing universe. Although we have made progress in our comprehension of space, Pluto's situation highlights our persistent gaps in knowledge. Grasping the gravitational effects of massive planets on Pluto's path offers essential insights into the broader mechanics of the solar system. It illustrates how the existence and position of each planet can influence the stability and course of other objects within the system. Despite these intricate forces, leading astrophysicists are expressing concerns about a possible collision between Pluto and Neptune. Neil deGrasse Tyson, a distinguished astrophysicist, provides a unique perspective on the enigmas of our solar system, particularly concerning Pluto. Tyson, famous for reclassifying Pluto as a dwarf planet rather than a full planet, shares enlightening thoughts on how our understanding of celestial dynamics is continuously advancing. He perceives Pluto's reclassification not as a diminishment but as a necessary shift in light of our growing knowledge about various bodies orbiting the Sun. His approach to celestial dynamics emphasizes ongoing learning and adaptation. He regards the intricacies of orbits like Pluto's as a reminder of how much more remains to be discovered in space. Tyson argues that the fascination with these uncertainties is what makes astronomy so appealing. He also acknowledges how events and discoveries related to space capture public interest in astronomy. He considers incidents like Pluto's reclassification and its unusual orbit as chances to ignite the public's imagination and curiosity about the universe. By discussing the dynamic and often counterintuitive elements of space mechanics, Tyson aims to cultivate a deeper understanding and appreciation of the cosmos. Neil deGrasse Tyson opens a portal for the general populace to marvel at the marvels and mysteries of the universe. Working alongside other scientists, Tyson actively alerts the public to the potential dangers of Pluto's erratic trajectory. After thorough examination of Pluto, he has raised alarms that the three-body problem could pose a real threat, suggesting that a collision with Neptune is overdue. Furthermore, Tyson stresses how such an impact could disturb the balance of the universe and lead to catastrophic repercussions extending even to Earth. A collision between Pluto and Neptune would be an extraordinary and disastrous occurrence in our solar system, releasing an enormous amount of energy that could likely fracture Pluto due to its smaller size and icy makeup. Debris from the collision might scatter throughout the solar system, posing potential risks to other planets and their moons. For Neptune, such an event could potentially alter its atmosphere and orbit, depending on the specific dynamics of the collision. Michio Kaku, a well-known theoretical physicist celebrated for his contributions to string theory and science communication, provides a distinct viewpoint on this situation. His insights into the future of space exploration and the connection between celestial mechanics and theoretical physics offer profound understandings of phenomena such as Pluto's orbit. Kaku views the examination of Pluto and its path as a window into the future of space exploration. Understanding the complex gravitational interactions and orbital dynamics of celestial entities like Pluto can, according to Kaku, yield vital insights for forthcoming space missions. This knowledge can enhance navigation through the solar system, predict potential hazards, and aid in planning missions to the outer reaches of our solar system and beyond. Kaku emphasizes that the insights gained from studying Pluto's orbit can be applied to investigate other celestial bodies, creating a framework for approaching and comprehending distant worlds. In discussing planetary physics, Kaku frequently highlights the deep connections between celestial mechanics and theoretical physics. He believes that the movements and interactions of planets, such as the gravitational interplay between Pluto and Neptune, are not isolated phenomena but are intertwined with fundamental principles of physics. Kaku's research in theoretical physics, particularly in string theory, seeks to understand these principles at their most foundational level. He suggests that exploring the complexities of celestial mechanics, like Pluto's orbit, can illuminate the underlying laws of the universe. Similar to Tyson, Kaku has also discussed the potential collision, linking it to his theories about the universe. If Pluto and Neptune were to collide, it would signify a major event in astrophysics, providing a unique observational opportunity that could potentially enhance our understanding of string theory. String theory, which posits one-dimensional strings instead of point-like particles, aims to describe the fundamental forces and matter in the universe. A collision of such magnitude within the solar system could generate extreme conditions of energy and gravity, offering insights into the behavior of fundamental particles and forces under intense circumstances, a central focus of string theory. Moreover, the gravitational waves resulting from the collision could provide valuable data for testing string theory's predictions related to gravity and spacetime. While the direct effects on Earth would be minimal due to our distance from the outer solar system, the scientific ramifications of such an occurrence could be significant, potentially contributing to our understanding of the fundamental nature of the universe as explained by string theory and other theoretical physics fields. Pluto's orbit exemplifies the intricacies of celestial mechanics, showcasing both stability and chaos within our solar system. The unique features of its orbit, shaped by the gravitational influences of neighboring planets, especially Neptune, highlight the intricate and dynamic character of space. The universe contains many mysteries, and the three-body problem is merely one of them. Scientists anticipate other possible disasters as well. Although the probability of planets colliding in space is extremely low, it is not entirely impossible. The manner in which planets' orbits are affected by various factors, including gravitational interactions, is elucidated by the three-body problem. In certain celestial systems, like TRAPPIST-1, which features 7 Earth-sized planets, gravitational forces create a rhythmic pattern known as orbital resonances. Over time, these patterns can lead to instability in planetary paths, potentially resulting in collisions. Despite the crowded nature of systems like TRAPPIST-1, collisions are not currently occurring. Scientists closely monitor these systems to understand how planets influence each other's trajectories, especially when they are in close proximity. This understanding helps us to grasp the movements of planets in space. Rogue planets, drifting through space without a star to orbit, introduce another unpredictable factor. These planets, once part of a star system, are expelled due to gravitational disturbances or other cosmic events, such as the close approach of another star or dynamic instability in multiple systems. Over time, these wandering planets can traverse vast distances, potentially reaching regions far from their origin. During their solitary travels, there is a slight possibility of them intersecting with other star systems. If one of these nomadic planets enters another solar system, there exists a minimal chance of colliding with a planet within that system. However, Given the vast and largely empty nature of space, the likelihood of a rogue planet directly impacting another planet is quite low. The enormity of interstellar distances and the scarcity of planets in open space act as deterrents to frequent collisions. Moreover, rogue planets are relatively rare compared to the multitude of stars and planets in stable orbits, making such encounters even less likely.